Greetings everybody, this is Lazarus Moises, and the topic of this video is going to be the discussion on continuation diagrams and coexisting attractors for the Lorenz chaotic system. So, in our channel, we already have our previous video where we discussed extensively about the Lorenz chaotic system and how to compute its bifurcation diagram. Okay, so let me remind everybody, we are talking about a classic, very well-known chaotic system. It is three-dimensional, it has three parameters, and it has a very rich behavior. Of course, for its most common values of the parameters, sigma equals delta, 10, r equals 28, beta equals 8/3, we can compute the trajectory of the system numerically, and we obtain this time series, which as we know is a chaotic time series. And if we plot the phase diagrams, we obtain this very well-known butterfly-shaped double scroll attractor. So regarding the bifurcation diagram, right, I'm going to post a link regarding the original video in the description. Now, the bifurcation diagram actually is a diagram that depicts the qualitative changes in a system's behavior as we change a single parameter. Okay, so the whole point is to reveal information about whether the system behaves chaotically or not, for what values does it behave chaotically, and how do we have this transition to and from chaos. So the bifurcation diagram, on the horizontal axis, we have the parameter value we want to study, and on the y-axis, we try to depict the qualitative behavior for each parameter value. And we do so by pointing the intersections of the trajectory of the system, of the attractor if you like, with a specific plane of interest. Okay. So let me remind everyone the pseudocode for computing the bifurcation diagram. First of all, we're choosing a parameter of interest. We call it bifurcation parameter. Here it's the parameter beta. We initialize everything else, like the rest of the parameters, sigma and rho, and our initial conditions. And then we choose the interval of interest. Here I chose beta goes from 0.2 up to 1. Okay. And we choose a very small iteration step. This, the smaller the step, the more detailed the diagram is going to look. So now what we do to compute the diagram? We start from beta equals 0.2. Okay. We choose this value. We simulate the system for a considerable time, more than 1,000 seconds, I would say. We discard the first few seconds, which is called the transient behavior. Okay. And from the rest of the trajectory, we compute its intersections with the plane of choice. Okay. Here we choose the plane x1 equals 0, and we choose the negative direction because, as the trajectory moves, it cuts the plane one time going in and one time going out. We are only interested in one of these intersections, so either positive derivative or negative derivative. Here I choose the negative derivative. So once I found out all of these intersections, I plot vertically the points beta, the parameter of interest, and from this intersection with x1 equals 0, I can plot either x2 or x3, one of the other two states. And here I choose x3. So I plot all of these intersections vertically on a 2D graph. So after I finish with all of this, here is the interesting point. What do? Usually, we reinitialize the initial conditions. So after the simulation is finished, we choose the x0 initial conditions equal to the last value of this trajectory. And then we increase the parameter 0.2 plus some small value, and we repeat the same thing. Okay. So here is a big deal. This reinitialization is very common in bifurcation diagrams, but the whole point is that we have a completely continuous trajectory, and pretty much little by little we change the parameter. So we see this whole diagram as a continuous solution of the system where the parameters steadily changes. In the literature though, you will see some differences, whether you do this reinitialization or not. Okay. In some of the literature works, it is more common that we call the bifurcation diagram the diagram in which we do not perform this step. This is why I have crossed this out. So in most of the recent works, when we say bifurcation diagram, we say that each time inside the for loop we simulate the system again and again and again, but always starting from the same initial condition. Okay, so we don't do this step. So let's for example, do this procedure where we do not reinitialize. So this part is crossed out, right? Compute the bifurcation diagram, and we obtain something like that. Okay. So we have discussed about the meaning of the bifurcation diagram in the previous video. I'm gonna post it again in the description below. But what do we see here where we don't reinitialize each time? Okay, we have some clear periodic and chaotic regions. We see this sort of crisis phenomena where we go abruptly outside of chaos. We have a period doubling transition to chaos. So all of these phenomena that are very interesting. But if you see right here where I point with my mouse, you see that although we have periodic behavior here and there, as the parameter increases, for some reason we have some sort of abrupt jump in the position of the attractor. So the attractor intersects the plane x0 right here, and we change the parameter a little, and it jumps back up, and then it jumps back down. Okay, why the hell does this happen? And if you look closely, it also reappears around beta equals 0.7 here. You see some abrupt jumps from up and down as we transition to chaos. And actually, it's not very clear in the diagram, but here around 0.95, it reappears. This phenomenon happens again. We have some abrupt jumps up and down. So what the hell does this happen? Okay. Now, you won't see this in all systems, but sometimes you will come across this phenomenon. This is a very clear indication that probably there are coexisting attractors in the system for these parameter values. What is a coexisting attractor phenomenon? The coexisting attractor means that attractors, plural, it means that depending on the initial conditions that we choose for the system, our trajectory may end up in different positions in the state space. Okay, this means that one initial condition may lead around here, another initial condition may lead around here. So we may have two coexisting attractors happening depending on the initial condition. And mind you, this may be different types of attractors. Like they may be coexisting both chaotic, they may be coexisting periodic with chaotic. So we're going to discuss this in a future video, because in this situation we're going to have a bit of symmetric behavior, where both attractors are either both periodic or both chaotic. So let me give you some examples. For example, let's run different initial simulations for different initial conditions for values around here or around here or around here. So for beta equals 0.5, here I have two solutions of the system. From different initial conditions, I have discarded the transient behavior. And you see they are both periodic. They are both very symmetrically looking, obviously, but they are at different positions. Okay, so different initial conditions lead different attractors in the state space. So this is an example of a coexisting behavior, right? Let me show you another example. Same example, I'm sorry. You will see that the intersections with the plane appear at two different positions, right? And that we are trying to depict in the bifurcation diagram or the continuation diagram that I'm going to show you later. Okay, we want to depict these two different coexisting behaviors. For another parameter value, 0.58, again we have this sort of symmetric attractors coexisting for different initial conditions, right? And again, if we look at the intersection with a given plane, x equals 0, we see that the intersection noted in yellow and in black appear at different positions. So I want to create a diagram that will manage to successfully depict both of these behaviors. Another example right here for beta equals 0.968, two different initial conditions, two different attractors. Okay. In all of these situations, they are very symmetrically looking in shape, but for any different chaotic system, this is not the standard case. Okay, you may not have this behavior. So I want to create a diagram that will manage to depict this coexisting behavior. How am I going to do that? Okay, this diagram is called the continuation diagram. Okay, the code is exactly the same as before, but see what happens. Once we finish up with finding out the intersection with a given plane, we reinitialize. We set the x0 initial conditions equal to the final value of our trajectory. Okay. Some people in the literature call this the bifurcation diagram, but in more recent works, the description is more consistent. This is traditionally called continuation diagram, and we do so in a forward loop. meaning that I start from 0.2 and I increase the parameter little by little until I reach the parameter beta equals 1. Okay. So this is called forward continuation diagram. I'm increasing the parameter, okay, and I'm reinitializing the initial conditions each time. And I obtain this graph. This is exactly as I showed you in our previous video. Okay, so this is much more smooth now. Okay, we don't have this sort of abrupt changes in the position of the diagram. Okay, and of course we managed to successfully depict periodic behavior, period 1, period 2, period 4, or whatever, and of course the chaotic behaviors right here. I'm giving you 3 examples of 2 different periodic behaviors and 1 chaotic behavior. Okay, so all of this is nice, right? So now, how can I find out coexisting attractors and depict them in the graph? I will do so by overlapping another diagram above this one. And this diagram is the exact same one I reinitialize in each iteration, but I move in a backward fashion. By that I mean that for this interval of interest, I start by setting beta equals 1, and then I go in a backward fashion. I will decrease the parameter. Beta equals 1, beta equals 0.1999, 0.1998, up until I reach 0.2. Okay, so this is called the backward continuation diagram because I'm starting from the maximum value and I'm moving backwards. All right. After I compute this diagram, I will overlap both of these diagrams. Okay, see what happens. So this is the result. The forward is in blue and the backward is in red. Okay. So it looks nice. Let's see. Did we really manage to, depict both coexisting attractors in all of these regions that we found out before? Well, in this small region right here that I showed you in the original bifurcation diagram, you see that we actually managed this. So if you look around here for the forward case, we have a transition to chaos by period doubling, that is right here. And in the backwards continuation diagram, we have a transition to chaos that appears right here. So here we clearly have coexisting attractors, right? We managed to depict that in our graph. In these regions, though, from 0.4 to 0.8, this region, and this region right here, where I have noted them in gray here in the original bifurcation diagram, okay, we know that possibly quadractors exist because we see these jumps right here, but did we manage to depict that? No, unfortunately, we failed to depict the coexistence of attractors. What does that mean? Does that mean that we really failed? Well, not really. And the reason I'm showing you this is because, this is a very good technique, but you should keep it in mind for all of the chaotic systems that you are possibly going to study. There is no like horizontal method that will work all the time and will perfectly give results all the time. Okay. This technique with forward and backward continuation works great most of the times. Okay. In that situations right here where we didn't manage to depict the bifurcation diagram, what can we do? We can simply try to look for coexisting attractors again, but a bit more carefully in the ranges of interest. Okay, so here we didn't really fail, but we didn't manage to depict all the coexisting attractors. We managed to depict them only in this region right here. So what I'm going to do, I'm going to use a continuation diagram again, but instead of studying this complete region of interest, I'm going to take a closer look, zooming in into this region that I know coexisting attractors exist, and into this region that I also know that we have coexisting attractors. So what am I going to do? I'm going to go into this region and I will try to find from 0.44, 45 around here that I'm going to start looking, 2 different initial conditions that give me different coexisting attractors. Okay. The idea is this. I will start the bifurcation diagram from different attractors, the continuation diagram, I'm sorry. And the idea is that as I'm increasing the parameter little by little, the diagram will sort of get trapped, if you like, inside the attractor, the different attractor each time. So I will start from one attractor, and as I'm increasing the parameter, the system will remain into these attractors spanning from the previous one. Okay, and I will do the same thing, but I will start from a different attractor this time. So I'm doing this by doing this exact same thing. I set beta equals to 0.44, which is my parameter of interest. I simulate the system and I obtain the blue attractor, right, for these initial conditions. So now what am I going to do? I try different initial conditions and see if I have a different attractor. For 0.1, 0.1, 1, for example, I obtain the same attractor in blue. I don't like that. So I will try a different initial condition. 0.1, 0.1, 2. I obtain the same attractor, so that's not good enough. I begin, I try again 1, 2, 3, 4, 5, 6, 7 different values, and then I try 0.1, 0.1, 5. And I simulate the system and I obtain the red attractor. So by this simple trial and error procedure, I managed to find out, I'm sorry, 2 different coexisting attractors for this parameter, right? So I will keep these initial conditions, and what I'm going to do is this. I will do 2 forward continuation diagrams. In this situation, I don't need the backward one. In some other case, I may need, but here I will do both forward continuation diagrams. The blue one is going to start from this position that I found the blue attractor, and the red one is going to start from this initial condition where I found the red attractor. Okay, and for both diagrams, of course, I will have this additional step which I re-initialize in each iteration. So let's run this and see what we get. And thankfully, we get this result. I'm sorry. So for this region right here, I managed to actually depict coexisting attractors. And we see that we have a pretty symmetrical behavior. So in one case, I have a period doubling root to chaos, which is the blue shape, and the red shape is exactly symmetrical in the continuation diagram, but it appears at a different position. Okay, so we have a period doubling root to chaos, some abrupt gaps right here, and then the 2 attractors end up merging together into a bigger one. Okay, and I did the exact same thing for a different region of interest. I did this small region right here. Again, I tried to find 2 coexisting attractors, and then I used 2 different continuation diagrams in the forward sense. Again, I obtained this coexisting behavior right here that wasn't present in the original diagram. Again, we have period doubling root to chaos until the attractors merge together. And then for the next region, this region right here, I did the same thing. And again, I managed to depict the 2 coexisting attractors. So you see, although initially in my forward and backward continuation diagram, I didn't manage to depict those regions, no worries. I just simply took a closer look. I did some trial and error, and I managed to depict both coexisting attractor regions. Okay. So depending on the system that you are studying, you should approach this the same way. Okay. There is no horizontal method that you will simply perform a diagram and everything will work perfectly. Okay, you need to go maybe a bit back and forth and try out different values. Okay? And in some situations where we have multiple coexisting attractors, multistability as it's called, we may also use different types of diagrams that will manage to depict all of the coexisting attractors for some specific parameter. But we are going to show this in a future video. So that's enough for now. Thank you very much, and I'll see you in a future video.